Estimating with finite sums is a little bit complicated. The whole idea is new, and the actual minutia of the calculations can be very difficult to come up with all the numbers. So here's a bonus lesson that reviews the big ideas and maybe extends a little bit. So maybe after doing a little bit of the homework, you might want to look back at this and give yourself a little bit more knowledge and a little bit more experience on really using finite sums. A picture. This lesson starts off with a picture of some kind of upside down looking parabola type thing and asks a few questions. Consider the diagram above in which rectangular approximation is being used to estimate the area. So to see what's being used, just look at each rectangle and see which side of the rectangle actually hooks up with the curve. And you'll notice each of these rectangles, I'll just choose this one here, there's a rectangle, and that rectangle, where it hooks up with the curve, is on the left side of that rectangle. That's one of the choices that can be made. You can hook up with the left side, you can hook up with the middle, or you can hook up with the right to do your rectangle work, all of which will give you an estimation of the answer, and in certain situations, each one will be a little bit better. Your first guess might be that MRAM would often be the most accurate choice, but MRAM can be the most difficult one to do. So MRAM often most accurate, usually most difficult to do. But as you'll find out, for our purposes, mostly it doesn't matter. We're just trying to come up with an estimate, so it doesn't really matter which one we use. But this one, because they're using the left-hand side of the rectangle as the defining value for height on the curve, then it's called LRAM. How many sub-intervals were used? Well, you just count up the rectangles. See, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 rectangles that are being used. So that was the number of sub-intervals that this curve was cut into to do the calculations. Now, it's been cut off on this one, but hopefully on your note you can see that on the scale you see a 0.5 for that one, and then a 1.0, and then a 1.5, and a 2.0, a 2.5, and a 3.0. You need those values to know what was the width of each subinterval. And apparently two subintervals is 0.5, so each subinterval here was 0.25. Now, the other way to get that value, and that can be useful moving forward, is to say, well, there was a total of 3 seconds, or 3 x, a width of 3 on the x that this curve was measured, and that was divided into 12 subintervals. So then, of course, each interval should be 0.25. Now, sometimes we use that as a fraction, as 1/4 as well, but the decimal on the scale here sort of led us to a decimal here. Next question, will the approximate be an underestimate or an overestimate? And you can see by the way this curve is and the way the rectangles are, that the rectangles each time are overestimating the area by a little bit. There's a little bit of chunk of the rectangle that's sticking out every time. So in this particular case, with the decreasing function, LRAM will overestimate. And on what interval is the approximation being made? Well, we're going from 0 to 3 there, so 0 up to 3. The other way to write that would be 0 less than x less than or equal to 3. Okay, so one with an equation instead of a graph. Paulus is using LRAM to approximate the area between the curve x cubed plus x plus 7 and the x-axis on the interval 1 to 5. So if Paulus wishes to use 100 subintervals, which would be really difficult to actually do in practice by hand, but let's say he did want to use 100 subintervals, what will be the width of each interval? Well, the total width that we want to do is 4. So we're doing a width of 4 for the whole interval. So to find our delta x, we take this width of the interval and we divide it by how many subintervals we want to get here. So I've got a total x interval of 4, and I want 100 subintervals, and that tells me that each subinterval should have width 1/25. Now, this question doesn't ask you to do the whole area. It just asks you to practice coming up with these rectangles, because it asks you what will the area of the third rectangle be. And that's the part that's really not easy in all this, is coming up with those values. So I'm going to do as I did before and draw a really big picture here that goes from 1 onwards. And hopefully you saw in the other examples that we really don't need to draw the whole thing from 1 to 5 to get the certain rectangles we want. See, I don't know exactly where this function is, and I'll just make something up like this and say, well, it looks something like that. And then I look at the rectangles that I would use for LRAM. So for instance, okay, well, you first use the subintervals to get the scale along the bottom, is if it starts at 1, that's what the question said, go from 1 to 5, and the width is 1/25th, well, then my next one is going to be 26/25ths. You know, that 1 is 21, or sorry, it's 25/25ths. I'm just going all over 25ths here to keep it accurate with fractions. And then I'll need a 27/25ths. And then I guess I don't know yet whether I'm going to need 28/25ths. And as you get more experience drawing them, you might know what's coming here. So they want the third rectangle. So the first rectangle would hook up there on the left side, and there would be my first rectangle. And I don't really care about that rectangle in this case because I'm looking for the third rectangle. Second rectangle would be evaluated there. And so there's the second rectangle. And then my third rectangle would be right there. Now I've narrowed down that third rectangle. So I guess I really didn't need 28/25ths, but maybe I didn't know that I didn't need that. And so for me, I get the coordinates of that point. That makes it easier for me to see what's happening, is the coordinates of that point would be 27/25ths would be the x value. That would be the left-hand side of that rectangle. And then the y value, I got to sub that 27/25ths back into the equation. So I got to sort of write sideways to fit this in here. So it'll be 27/25ths. I got to cube that. And then plus a 27/25ths plus 7. That would be the y value. And I'm just taking that x value that I decided would be the left-hand x value in that interval and just subbing it back into the y value. So my area of that third rectangle is just base times height. And the base of each rectangle is 1/25th wide. I found that out above. And the height here is the y value on that rectangle, which would be this 27/25ths cubed plus 27/25ths plus 7. You know, that whole thing multiplied together. And let's just practice typing that in the calculator here. Where did I put my calculator? There it is. Okay, so the area I found was first the width of the rectangle, which is 1/25th. Close the bracket. Now the height, open bracket for the height, and then I got to do, 27/25ths. And that's got to get cubed. Then plus a 27/25ths. And then plus 7, close the bracket, and I get a decimal answer there, 0.37358848. Back to my... So that one got so messy that it couldn't really be expressed as a fraction very easily, so we switch over to decimals there. Okay, so that was third rectangle. I mean, we found in the other part of the lesson that when you want to find the whole area, you'd have to add a lot of these things together. But this is just practice, picking off one particular area to see if you can come up with those numbers. Would the area of the third rectangle be the same if you used RRAM or MRAM? No, it would not be the same because we'd use a different value. For instance, for RRAM, we would have used the right-hand side of this rectangle as the value. So it would have used x equal 28/25ths. And MRAM would have used, well, halfway between 27 and 28 they would have used. So I don't know, that's 54, like 55/50 it would have used as its third rectangle. So it really does depend on whether you're using LRAM, MRAM, or RRAM, what you get for the value there. Like for the first rectangle, we would have used 26, then we would have used 27, then we would have used 28. So some of the same rectangles appear, but they appear at different times, and that's how you get underestimates versus overestimates. next one asks for use the calculator program. So we'll have to do that in class. We'll have to get those calculators in our hands and really see how the calculator program will do this. And actually, it's going to work pretty well to get some practice at doing this by hand and then see how the calculator works in class. Next question. Carmelita is using rectangular approximation to determine the area between a function f at x and the x-axis on the interval 0 to 2. To do so, she made the following calculation. So she did all this work here, and our job is to figure out what it is she did. It said how many intervals did she use, and if you just look at how many terms there is, there's 1, 2, 3, let me count them, 1, 2, 3, 4, 5, 6, 7, 8 different terms that she used. Now, the next question is, what is the width of each interval? Well, there's two ways to pick out the width. One is to say, well, listen, the interval is 0 to 2 wide, so the delta x is the 2, the whole width of the interval, divided by how many intervals we'd like to do, so the delta x is 1/4. That 1/4 can also be seen, and let me highlight it, as the base of each of these rectangles. You see how that 1/4 is in every single term, so that's the base every single time. Did I highlight it 8 times? I want to make sure I get them all there. 3, 6, 8. So there's the base every time in the rectangles was 1/4, and you could see that in every single term. Now, is Carmelita using LRAM, MRAM, or RRAM? Well, let's just talk about the very first rectangle. We'll be able to nail it off the very first. She's going from 0 to 2, so I don't know exactly where this value of this rectangle is. I just want to talk about where that rectangle is evaluated. For instance, if you were using LRAM, you'd use the left side of this, which would be 0. If you were using RRAM, you'd use the right-hand side to evaluate, which would be 1/4. And that's what she did in the very first one. You see, there's a 1/4 there that she plugged in for calculating her y value. So she must have used RRAM to do her values, because if she had used LRAM, she would have started with a 0, not a 1/4. If she used MRAM, she would have used halfway in between. And then finally, what's the equation for the function? Well, I highlighted the one part in yellow, so I'm going to highlight the other part in green. That's the part that is the evaluation of the function every single time. And I'll just read it out loud, and hopefully the pattern becomes clear. Is 1/4 fifth to the power 5, ln 1/4, 1/2 to the fifth, ln 1/2, 3/4 to the power 5, ln 3/4, 1 to the power, it's always something to the power of 5, so the function must have been x to the power of 5, and then ln of that same value, so ln of x. So you just look at each piece there that you know is the height of each rectangle and use that to pick off whether she used LRAM, MRAM, or RRAM. So we've seen examples with the graph now and with the equation. Now here's one from a table of values. In some ways, using a table of values is easier, but there is a little different thinking that has to go along here. So here's some data, time 0, velocity 0, time 1, velocity 12, etc., all the way along there. And it says write an expression using LRAM with 4 sub-intervals to estimate the distance traveled. So when we use LRAM, it means we're going to use the left-hand side of each interval. So the intervals here, if we're going from 2 to 6, see, they just want 4 subintervals. So the 4 intervals are 2 to 3, that's the first subinterval. 3 to 4, that's the next subinterval. Oops, 2. 4 to 5, that's the third subinterval. And then 5 to 6, that's the fourth subinterval. So we're evaluating from 2 to 3. From 3 to 4, from 4 to 5, and from 5 to 6. Those are the 4 subintervals we're going to use to go from 2 to 6. Now, if we're using LRAM, that means we're going to use the left-hand side of the interval every time. So every time we go to an interval, we use the left-hand value to evaluate for that interval. So distance equals, okay, so every time base times height. Every one of these rectangles, every one of these intervals is 1 second wide. That is, we're going 2 to 3, 3 to 4, 4 to 5, 5 to 6. So base is 1. Then the height will be whatever it is at the left-hand interval. So in interval 1, we use 2 as the left-hand interval, as the left-hand value. Because in interval 1, the left-hand value is 2. So we want the value at 2, which is the 22. Then, second interval, still with 1, but now we do left-hand interval of 3 to 4, which is the 10. Then, with 1, left-hand interval of 4 to 5, which is the 5. And then the last one, still 1 wide, left-hand interval, left-hand value for 5 to 6 would be the 13. If that is a little difficult to decipher, let's just talk about the one section. That is 2 to 3. I'm going to over here go from time 2 to time 3. There's 2 different values we could use. We could use 22 or we could use 10. Those are the 2 values we have for that section of the graph. So we decide in this question that they were using LRAM, and LRAM would say use the one on the left-hand side there, which is the 22. And that's how we got to the 22 right there. Then when you go 3 to 4, you got a choice between 10 and 5. You choose 10 because you use the left-hand side. So this uses the left-hand side every time. And when I add all those up, what do I get? 22 and 10 and 5 and 13. I think I get 50 meters when I add all those up. So basically what they're saying is, in other words, we're saying what we're going to do for our estimate is assume that from the time interval 2 to 3 that they were going 22 inches per second. Ooh, inches. Whoops. They were going 22 inches per second that whole time interval 2 to 3. And then from 3 to 4, we're going to say they were going 10. That's our estimate, is that they were going 10 inches per second. And then from 4 to 5, they were going 5. And then from 5 to 6, they were going 13. So just in each interval, we choose one of the values, either the left-hand value or the right-hand value, to estimate their velocity through that whole interval. And while you're doing that, you might be thinking, well, I can think of better ways to do that. Yeah, absolutely. There's plenty of better ways to do that. This one just asked for LRAM. Let's do it again for RRAM. For RRAM, again, we'd have distance, and each rectangle would be 1 wide. So there's the first interval, and then the second interval, and the third interval, and the fourth interval. And let me just handle this just a little bit differently, just in case that explanation wasn't very good for you. Since we're using RRAM, this interval right here, I'll just put a little notation of this, in here would be the 2 to 3 interval. And in here is 3 to 4. And in here is 4 to 5. And in here is 5 to 6. That's what we want to put in there is a value for the velocity for between 2 and 3 seconds. But if we're using RRAM, when we look from 2 to 3 seconds, we're not going to use 2, we're going to use 3, the right-hand side. So this time I get 10 in there. And then from 3 to 4, I look and go, okay, from 3 to 4, it goes from 10 inches per second to 5 inches per second, but I'm going to use the 5 because we're using RRAM here. Then from 4 to 5, it goes from 5 inches per second to 13 inches per second. I'm using RRAM, so I'll use 13. And then 5 to 6, it goes from 13 to 11. And because I'm using RRAM, I'll use 11. So my total distance here is what? 10 and 5 and 13 and 11. And I get 40 when I add all those up. Oh, no, 39. Let's see. 15, 28, 39. Yeah, 39. 39 inches. Okay, so up here my estimate was 50, but down here my estimate's 39. The actual answer is probably somewhere in between those two, but now I've got an upper and a lower to work with. And the last question for this one is, can we write an expression for MRAM for using 4 subintervals? And yeah, we could. We could write it. Here's how we could do it. We get the original table, time and velocity. And instead of all those time intervals, to use MRAM, I'm going to put time intervals in between. I'm going to go 0. Oh, wait, I don't need 0. We're doing 2 to 6, right? So, okay. So I'll start at 2. 2, 2.5, 2.5, 3, 3.5, 4, 4.5, 5, 5.5, 6. And if you were thinking earlier about ways to do this, get a better estimate, this might have been one of the ideas you had. So I don't have all the data. I've got, for 2, I had 22. For 3, up above it says 10. And then for 4, it says 5. And then it says for 5, it says 13. And then for 6, it says 11. Now, you don't have the data in between, so we could estimate. Instead, I'm going to write that in there and say, well, we're really reaching now. We're doing an estimate of estimates here. But instead of using the left or the right, maybe I could use like an average of those two and say, okay, well, an average would probably be a better estimate of these. So I'd use like 16 and 7.5 and 9. So, just halfway between those values. And then I could use this as my value for MRAM. And I can't resist finishing this off, even though it didn't really ask for it. So 1 times 16 plus 1 times 7.5 plus 1 times 9 plus 1 times 12. And what do I get? 16. Ooh, I switched over to A there. That's funny because we're doing so much with area, but this is distance. Plus 7.5 plus 9 plus 12. I get 23.5, 44.5 inches. And that's probably the best estimate we've got so far from what we have. This is all estimating. And so that was somewhere between the 39 and the 50 and a much better estimate there. So could you? Yeah, you could do a little bit more estimating here and probably do a little better using MRAM. Okay, last of these examples. These are wild, but it will show off. We just can't even resist in these even in the first section of integrals to show off some of the power of this method that we've used. Because you might look at this and go, well, wait, where's the rectangles? And I'll talk about rectangles in the middle of all this because there is some of the old method laying here in all this. So the idea is, imagine you take a parabola and you rotate it around and you make a shape, and you have to be able to visualize the shape first of all. It would be sort of a sideways vase that we're looking at, three-dimensional. If you take that blue line and rotate it around, just picture a 3D little chunk there that would have a volume instead of an area. And the method we use is to say, okay, we're going to take that volume, that shape, and again, I think only really the only shape I can really think of is a vase of what we're looking at. If you just look at this sideways, you'll see, okay, sort of standing up like that. I don't know how this vase would stand up. It's got a really circular bottom, but that's the sort of shape that we're trying to find the volume of. And to estimate it, what we're going to do is build little cylinders, because cylinders are pretty easy to find the volume of. And so we're going to estimate that volume with a bunch of cylinders. Now, when you look at the picture, you might be like, well, the way you've drawn it with that many cylinders, it's not going to be a great estimate. Again, we're building towards something, and we're going to get lots of cylinders. By hand, we don't want to have to do more than about 5 cylinders. In fact, you might not even want to do 5 cylinders. So the idea that this isn't a very good estimate, we'll take care of that in later lessons. For now, let's just say that it's going to be a decent estimate. It's not going to be that bad. It's not way out of sight as far as the estimate of this really strange paraboloid, it's called. It's a paraboloid because it's a three-dimensional shape built by taking the parabola and spinning it around the x-axis. You're going to see a lot of these type examples coming up. So if this is completely weird and you make only a little bit of progress on the visualization, that's okay, because we're going to see lots of these. So it says, estimate the volume of the paraboloid using LRAM with 7 cylinders of equal height. 5 cylinders of equal height. So there's only 5 cylinders here to do. So let's talk about each of those cylinders in turn. Now they said used LRAM, so that changes the calculation slightly. Now let's just talk about what we're adding up here. To find this whole volume, we're going to do the volume of each of these cylinders. So there's going to be a pi times the first radius times the height. Then there's going to be pi times the second radius squared times the height. And then pi times the third radius squared times the height. And then pi times the fourth radius squared times the height. And then pi times the fifth, times the fifth radius squared times the height. So just 5 different cylinders that I'm going to add up all their volumes. Each one has volume pi r squared times the height. So what we've got to do is find each of those radii that we're going to calculate, because the height's easy. the height of each of these cylinders, because of what we've chosen here, it's interval 0 to 5, and we've done 5 intervals. So the height of each cylinder is 5 divided by 5 intervals. It's exactly 1. So let me just fill that in there. Pi times some radius squared times the height, which is 1. And then pi times some radius squared times the height, which is 1. Now, when you're doing these questions, this really helps me, is to take care of this part of it. And I'm just going to jump onto the last line there. This really helps me to frame what it is I'm doing and really focus on what I got to figure out, which is the radius of each of these cylinders, because their height's all 1, and pi is going to be the same all the way through. So let's talk about the radius of each cylinder. Now, the radius of the first cylinder, because we are evaluating at 0, its radius is 0. So we get this first cylinder, which really doesn't even exist. There's not even really a cylinder we're going to use to do that first estimate, which might lead you immediately to go, LRAM's a really bad choice here. Why wouldn't we use RRAM? And I'm totally with you. This one just asked you to do LRAM. And again, just like previous examples, maybe RRAM would be better, maybe MRAM would be better. Of course, more intervals would be better. But this is just for practicing and getting used to the method. Now, this is where it gets interesting. It seems like it's going to be really difficult, and it's not. Because this point right here would be 1, comma, well, that's just a parabola. So to sub the 1 in, we'd go root 1. And I'm going to leave it as root 1, again, just to establish the pattern. I know that root 1 is 1. I know that. But I'm just going to put that in there like that. But notice that y value is the radius. Each of these cylinders, that y value that we're talking about, is the radius. So if we find each y value, we found each radius. So the second radius really here is root 1. Then this next one, we're evaluating now at x value 2, and I want to find that y value, so I sub it into the original function, so that's root 2. And again, that y value is just the radius. I don't know how many of these you want to do. It's the same every single time. This next one is 3, sub it in to get root 3, and so the radius is root 3, and then finally root 4. And that would be awesome by itself. But look what happens here. Pi times 0 squared to 1, that's 0. Root 1 squared is just 1 times pi times 1. That second term is just pi. The second term, well, root 2 squared is just 2 times pi times 1 is 2 pi. And then the next one I get 3 pi, and then I get 4 pi. What a nice set of terms I get here, and I get my approximate volume of 10 pi. Let's just put that on there to make sure we understand that the volume isn't exactly 10 pi. It's not quite that beautiful, even though the answer is pretty beautiful. It's not much worse than this when we actually get there. And we're not far away. We're only a handful of lessons being able to get this exact volume, and we have our volume estimate of being 10 pi. Incidentally, if you did RRAM, you'd have all of these terms still, and then you'd have the 5 pi at the end, so your RRAM would be 15 pi, which is kind of interesting. I just throw that in there, that LRAM and RRAM are really connected, just the first and last term is different, and we're going to talk about that a little more later. Okay, so that puts us into 3 dimensions and maybe really opens up the possibilities here and go, this isn't just about areas. We can do volumes. We can do a lot of different things. We've already found out we can do distance. So this integral that we're talking about, which is just the adding up of these rectangular pieces, and in this case, these cylindrical pieces, has some pretty unbelievable power here. Last question in this video. If 50 cylinders of equal height are used to approximate the volume, what would be the height of each cylinder? So if we want to find those individual heights, instead of going from 0 to 5, so that width is 5, in 5 cylinders, we want to do it in 50 cylinders, so we'd have a height of each cylinder of 1/10, and maybe we'd be over to 0.1, depending on whether we wanted to get exact answers for our approximation or whether we were willing to round off. It just depends on what we were trying to accomplish there. We'll see how to do this with a computer program in class, or a calculator program in class, and once we have it in the calculator program, we can easily go from 5 to 50 to 100 different intervals pretty easily. So that'll be pretty nice to get that kind of power available once we get that calculator back in our hands and ready to rock and roll, and make sure that calculator program is loaded up. Well, I'm hoping those examples will help you through some of that homework. So after you check out this video, then go back and maybe relook at some of the homework you had trouble with, or get ready to attack some of the tougher problems in the homework. Have a great day.